Our universe, an endless expanse of galaxies, stars, and cosmic mysteries, had a surprisingly explosive start. This wasn't your typical explosion, though. It wasn't an explosion of matter into pre-existing space. No, this was a rapid expansion of space itself. Just imagine, in a fraction of a second, what was essentially a singularity expanded exponentially to become the universe we know today. Now, this isn't just some wild speculation. The Big Bang theory is backed up by a powerful combination of theoretical physics and direct observations by astronomers. You see, theoretical physics provides us with a mathematical framework that describes the universe's behavior. And lo and behold, when astronomers look through their telescopes, they see a universe that behaves just like the equations predict. But what was the universe like just after the Big Bang? Well, it was hot, dense, and brimming with energy. So much energy, in fact, that light couldn't shine through. It was a state of existence so extreme that it's difficult for us to fully comprehend. But as time passed, the universe cooled down, allowing atoms to form and light to shine. In the blink of a cosmic eye, our universe went from a hot, dense point to a rapidly expanding space filled with energy. Now that's an explosive start if ever there was one. And all of this happened approximately 13.8 billion years ago. So, the universe started with a bang, not a whimper. But what happened next? Stay tuned to find out. Greetings, fellow cosmic explorers. Welcome to Cosmic Science Fiction, the channel where we embark on mind-bending journeys through the vast realms of the unknown. I'm your host to the mysteries of the cosmos. If you've been enjoying the cosmic wonders we've been uncovering together, don't forget to hit that like button. It's like fuel for our spaceship, propelling us further into the depths of science fiction's uncharted territories. And of course, if you haven't already, be sure to subscribe to Cosmic Science Fiction. Hit that subscribe button and join our crew on this interstellar adventure. By subscribing, you're ensuring that you never miss out on the mind-boggling content we have in store for you. After the Big Bang, the universe didn't just stop, it kept growing but at a slower pace. Just imagine, space itself was expanding, not into anything but rather, everything was getting further apart within it. This might be a bit mind-bending, but that's the beauty of our universe. Now you might be wondering what was happening during this slower expansion phase. Well, a lot actually. You see, during the first 3 minutes of the universe's existence, something incredibly vital happened. This period, known as Big Bang nucleosynthesis, witnessed the formation of light elements. You've probably heard of a few of them: hydrogen, helium, and small amounts of lithium. These were the first elements to ever exist, the building blocks of everything we know today, and they didn't just pop into existence out of nowhere. No. They were formed from the primordial soup of protons and neutrons that filled the universe in its infancy. But here's the catch: while these light elements were being formed, the universe was still a blazing hot inferno, too hot for light to shine through. It was a strange paradox, a universe filled with the elements of light yet plunged in darkness. And all this happened in just 3 minutes. Yes, 3 minutes into the life of our universe. It's amazing, isn't it? The universe was not even a toddler yet, and already it was cooking up the elements that would one day form stars, planets, and even life itself. 3 minutes into the universe's existence and we already have light elements. But it was still too hot for light to shine. Imagine a universe too hot for light to shine, a universe in darkness. Welcome to the Dark Age. Just picture it, a universe ablaze, a furnace so intense that it was impossible for light to exist. This was the universe during its Dark Age, a time when the universe was still in its infancy and too hot and dense for light to shine through. But as with all things, change was inevitable. The universe began to cool, and as it did, wonders started to occur. The temperature dropped to a point where protons and electrons could finally come together, forming the very first atoms. Now this might seem like a simple process, but let's not forget. These were the first atoms. They were the building blocks of everything that we know, everything that exists. This was a game changer. With the formation of these atoms, the universe was no longer a hot, dense soup of particles. It was becoming more structured, more ordered, but it was still dark, still devoid of light. So what changed? How did we go from a universe of darkness to one filled with the brilliant light of countless stars and galaxies? Well, it's all thanks to these newly formed atoms. You see, when atoms form, they create a sort of shield that can absorb high-energy photons. These absorbed photons are then re-emitted as lower-energy photons, or as we like to call it, light. And so the universe began to light up, slowly but surely. It was a gradual process, one that took hundreds of millions of years. But eventually, the darkness began to recede, replaced by the soft glow of the universe's first light. This was a pivotal moment in the history of our universe. It marked the end of the Dark Age and the beginning of a new era, an era of light and structure. And after 400 million years, the universe was finally ready for the first stars and galaxies. This momentous transition from an opaque, dense universe to one filled with light and matter set the stage for everything that was to come. From darkness to the first glimmers of light, we've now entered the epoch of reionization. Imagine a time roughly 400 million years after the Big Bang. The universe has cooled, and it's now a stage set for the birth of the first stars and galaxies. These celestial bodies didn't just pop into existence. No, it was a cosmic dance, a delicate ballet of elements, gravity and time. Atoms, once too heated and chaotic to form stable bonds, have now cooled enough to come together. Hydrogen and helium, the lightest of elements, began to coalesce under the immense pull of gravity. As these atoms amassed, they created dense pockets of gas, and within these pockets, the first stars ignited. The immense pressure and heat in their cores triggered nuclear fusion, releasing a burst of light and energy, pushing back the darkness that had reigned for millions of years. These first-generation stars, composed mostly of hydrogen and helium, were massive, hot, and short-lived. Their explosive ends scattered heavier elements across the universe, providing the raw materials for subsequent generations of stars and the formation of galaxies. Galaxies, these vast islands of stars, gas, and dust, began to form as gravity pulled these elements together. The first galaxies were likely small and irregular, a far cry from the majestic spirals and ellipticals we're familiar with today. But over time, these galaxies grew, colliding and merging with others, shaping the cosmic landscape we see today. But here's the thing, the birth of stars and galaxies didn't merely light up the universe, it also changed it. The ultraviolet light from these newborn stars started to ionize the surrounding hydrogen gas, creating what we now refer to as the epoch of reionization. This process, over hundreds of millions of years, made the universe transparent to light, allowing it to travel across vast cosmic distances. The universe was now a place of stars and galaxies, but a mysterious force was about to speed things up. Fast forward to 5 or 6 billion years after the Big Bang, something strange started happening. Our universe, which had been expanding at a steady, leisurely pace, suddenly kicked into high gear. The culprit? A mysterious force known as dark energy. Now, dark energy isn't your run-of-the-mill energy. It's not something you can see, touch, or measure directly. It's a theoretical term we use to explain a mind-boggling phenomenon, the accelerated expansion of the universe. Let's throw a dash of imagination into the mix. Picture the universe as a loaf of raisin bread dough. As it bakes, the dough expands and the raisins, our galaxies, move further apart. But imagine if that loaf suddenly started to bake faster, the dough expanding more rapidly, flinging the raisins apart at greater distances. That's what dark energy does to our universe. But why? That's the billion light-year question. What we know is that dark energy opposes gravity, the force that pulls matter together. Instead of slowing down the universe's expansion due to the gravitational pull of all the galaxies, stars, and matter it contains, dark energy has been pushing it to expand quicker and quicker. Yet, dark energy remains one of the most significant unknowns in cosmology. It's like the phantom of the cosmic opera, present yet elusive. Scientists estimate that dark energy makes up about 68% of the universe, yet we understand less about it than anything else. It's the ultimate cosmic riddle. A puzzle piece that doesn't quite fit, yet without it, our understanding of the universe remains incomplete. The universe, now about 13.8 billion years old, was expanding faster than ever, thanks to dark energy. This elusive, mysterious force continues to shape our universe, driving its expansion and challenging our understanding of the cosmos. It's a reminder that the universe still has secrets to unveil, cosmic mysteries yet to be unraveled. And isn't that what makes the exploration of space so endlessly fascinating? Our universe isn't just stars and galaxies, it's a mix of atoms, dark matter, and dark energy. Now this might raise eyebrows. Atoms? Yes, those tiny particles that make up everything around us, they account for only about 4.6% of the universe, imagine that. The rest is dark matter and dark energy, the silent, invisible giants of the cosmos. Now let's take a deep dive into the universe's structure. It's not just a random scattering of celestial bodies, there's a method to the cosmic madness. The universe's structure, including stars, galaxies, and voids, came into being through the gravitational pull of matter fluctuations. Let's break that down. In the early universe, matter was distributed almost evenly. But almost is the key word here. Tiny fluctuations, minute differences in density, gave gravity something to work with. Over billions of years, these small differences grew larger, as areas with slightly more matter began to collapse under their own gravity. These regions pulled in more and more matter, growing denser, and eventually igniting to form the first stars and galaxies. Meanwhile, regions with less matter were left behind. They became the voids, the vast empty spaces between clusters of galaxies. The result is a cosmic web, a network of galaxies and dark matter intertwined with voids. If we could see the universe from outside, it would look like a cosmic sponge. Dense regions of matter, where galaxies cluster together, are separated by vast, empty voids. This is the large-scale structure of our universe, a testament to the power of gravity and the passage of billions of years. But that's not all. The universe isn't static. It's expanding thanks to dark energy, a mysterious force that's speeding up this expansion. And this brings us to a fascinating question. So, what's the shape of our universe, you ask? The shape of the universe, it turns out, depends on a cosmic tug of war between expansion and gravity. Just imagine a never-ending struggle, a celestial arm wrestling match where the contenders are the forces of expansion and gravity. The outcome of this match determines the shape of our universe. The shape isn't something as simple as round or square, but rather, it's about whether the universe is finite or infinite in extent. There are three main theories that scientists have proposed. The first is that the universe is flat and stretches out infinitely in all directions. Think of it like an endless sheet of paper. This is supported by observations that show that on large scales, the universe appears flat. The second theory is that the universe is curved, like the surface of a balloon. This would mean that if you traveled in a straight line for long enough, you would eventually end up back where you started, much like walking around the Earth. The third theory is that the universe is saddle-shaped. This is a slightly more complex shape to imagine, but it's essentially a universe that curves in one direction like a saddle, and in the opposite direction like a Pringle chip. Each of these shapes is a result of the battle between expansion, driven by the mysterious dark energy, and the pull of gravity. If gravity wins, the universe curves in on itself. If expansion wins, the universe is flat or saddle-shaped. But here's where it gets even more interesting. The universe could be any of these shapes and still be either finite or infinite. Even a curved universe could stretch out infinitely like an infinite stack of balloons. So which is it? Well, the jury is still out. Our current measurements suggest that the universe is flat and infinite, but there's a margin of error that leaves room for other possibilities. With our journey from the Big Bang to the present, we've unraveled the mysteries of our ever-expanding universe. And remember, the universe doesn't just tell us where we've been, but also where we're going.